Good morning, class. Today we're going to talk about potential energy. So we're going to share my class notes with you. There are actually different types of potential energy, and potential energy is just stored energy, something that's available to let us do some work in the future. For example, the gasoline in your car is stored energy. The food you eat is stored energy. It's chemical energy that we can use to transform into other types of energy. The types that we're more interested in at least in physics, is an object, the position of it, whether it's going to roll down the hill or a bicycle at the top of the hill or something like that, or something falling. Those are all potential energy due to its position. And then we have elastic potential energy. And we're going to spend quite a bit of time on that. That would be something like a spring has potential energy in it. It's got an energy that is stored in it. So the formula for the one that we're going to use quite a bit is the gravitational. And it's just very simply mass times gravity times height. And we'll be able to get joules with that. The other formula that we're going to use is elastic potential energy. And this was one maybe that you're not familiar with, where we have 1/2 times K, which is the spring constant, which we'll talk about in just a moment, and the distance that that spring is compressed or stretched. So if we want to look at that spring constant a little bit more and see what that means, is we're going to change to the document camera. And here we have springs, and that K value is how stretchy or how strong or how much force it takes to make that spring expand and compress. And see here's even a spring that would have not a very strong spring constant whatsoever. So think of it again, another way to think of it is you wouldn't want to use a spring that is in this pen and use the same springs that are on your vehicle. So each constant has a different value. So this value that we're talking about, how stretchy something is the spring constant. The other part we need to be concerned about is finding that X value, this value that we use in this formula. It's the distance that is the difference between when it's relaxed, when it's just like this, versus when you put the force on it and it's stretched out. The difference between the relaxed and the stretched out part, that is the X that we want to use in the formula. So another way to look at that and give you another visual of that is right here. Here I've got a system where I have my spring like this. This would be my relaxed distance right here. I stretch it out. The difference between the distances between stretched and relaxed, the difference between the two pencils, that is our X value that we would use in any of our problems. So I think the best thing that we can do now is let's go on to an example. So let's go back to the class notes. And I wanted you to take a moment with this example problem. I want you to go ahead, pause the video, and see if you can write out the givens. And then look at the problem carefully and see if you can see what types of potential energy we will have in this problem. So go ahead and pause it now and see if you can write it out. All right, welcome back. Mr. Kohlmeyer said I had to say the welcome back part like you paused it. So here is what we have. We have our bungee jumper. We've got the cord of the bungee that is just when it's relaxed is 15 meters. When the jumper comes to a stop, he has a stretched length of 44. The river itself is 50 meters. So one of the things that we have to take in consideration here is that this bungee jumper is sitting here hanging down at 44 meters. There is still potential energy between where he's hanging and where he actually can fall to the river, because at this height right here, there would be zero potential energy, but he actually still has some potential energy right here. And then we have the potential energy in the bungee cord itself. So some more of the given we have is the 70 meters or 70 kilograms that he weighs. We have the spring constant. We know that is how much springy or how much stretch force this actually has. We have the height that the bungee jumpers actually has above the water. And then we have the distance that the compressed or the stretched, and in this case, it's the stretched part of the bungee cord that we are interested in for potential energy. So again, we have the 6 meters he's hanging from. And we know that the potential energy, there are two types of potential energy in this problem. We've got him hanging here from above the water at 6 meters, so he could still fall 6 meters if he cut that bungee cord. And then the stored energy in the bungee cord itself. So here's how we write that out, showing that I have both types. Then I have, let's take care of the first one. He could fall this 6 meters, that height. So I just have his mass times gravity times that, I get my joules. Then the elastic, I have the spring constant that they gave me. And then again, I want to stress that I have the difference between the relaxed and the stretched length, which was 29. I add those together, and the potential energy in this system right here that we still have is 3.43 times 10 to the fourth joules. There's one more type of problem that we need to look at that's going to be in your homework, is with a pendulum. What happens with a pendulum and the energy that is still in a pendulum due to its position? So what we want to look at here, what I'm talking about is if I have a pendulum, we know a pendulum just swings back and forth like this. When it's up here, this would be its maximum potential energy. We know here it would have both kinetic because it's moving, but it still has a potential energy to fall down to here. So we still have some potential energy here. And then we also have, at this point down here, there would be no potential energy. It can't fall anymore. It would be all kinetic energy. Then it would continue on, and the same thing would happen on this side. So what we want to look at closely is how do we get some of these values that we want to talk about? So again, we're talking about potential energy with mass times gravity times height. And the maximum height is equal to, this height right here would be equal to the length of the string. So if they tell you the length of the string is 2 meters, for example, then I would use 2 meters for my maximum potential energy. The interesting part, or the part that takes a little more work, would be if we're partway down. Let's say we're at an angle of 30 degrees. We still have some height that this pendulum can fall, and that, to figure out that height, is sometimes a little more difficult. So really what it is we want to know this one right here. It's a triangle. So it would be the length, the original 2 meters in this example, times the cosine of whatever angle that is. And that is what we would use for my height right there. And then again, if they ask what is the potential energy at the bottom, well, it's 0. It doesn't have any farther than it can fall. All right, so now you should be able to do your homework. You have on page 172, problems number 1 and number 3. And then on worksheet B, which is downloadable on the website, problems 1 through 7. And I put the answers up so you can check those, but please make sure you do those problems because we're going to move on. the next day and start talking about the conservation of energy, where we start combining potential energy, kinetic energy, and initial and final, and the problems are going to get a little more interesting. All right, have a good day.